All right, good morning, everybody. This was the last problem from that worksheet last week that we didn't actually finish. So I want to go through it quickly with you guys. I don't think I have the wording exactly right, but the gist of it was you mix these two soluble salts together, figure out the precipitation reaction, and then we're also taking a limiting and excess look at this reaction as well. So the reaction should be written as potassium iodide plus silver nitrate. Can we predict whether these are soluble or insoluble, whether these will be aqueous or solids? Just have to follow the precipitation rules, or the solubility rules. And in case you didn't get it last week, I still have more of our final exam cheat sheet, our final exam equation sheets, and that has these on there as well. Do you need one? So the solubility rules aren't necessarily something you have to memorize so much as be able to utilize this tool for. So generally soluble, silver. Potassium, not an exception. Always soluble, I'm sorry, that was a weird thing that I said. Generally soluble, iodide. Potassium, not an exception. Always soluble, nitrate. In lab, those of you that are in lab, last week we were doing precipitation reactions. One thing that I showed my lab students was that if you start the molecular equation and then start your net ionic equation, you can figure out your charges, you can swap the ionic pairs, and based on the charges, you can predict the chemical formulas of the products a little bit more easily. Here, everything has a +1 or minus 1 charge. So we get silver iodide and potassium nitrate as possible products. And I actually say possible products because potassium nitrate isn't a product of this reaction. Potassium nitrate is soluble. By saying that this is aqueous, we are saying those ions are not interacting with each other. They are interacting solely with molecules of water. Potassium nitrate, not really a product of this reaction. They haven't changed their chemical state at all. They started soluble, they ended soluble. Silver iodide, though, this is an exception to iodide solubility. So the precipitate that forms silver iodide. Now, the question is, which of these ions, silver and iodide, stays in solution? This is where we have to start doing the stoichiometry. So if I had 0.65 grams of silver iodide, my chemical equation is already balanced, so I really just need to know how much silver iodide can be made from my potassium iodide starting material. So on a roadmap, I'm going from grams of potassium iodide. The only way I can go is to moles of potassium iodide. From there, from moles of potassium iodide, moles of silver iodide, and I can actually stop there. I don't necessarily need to know the mass of what I'm making unless that's what it asks for. So grams of potassium iodide to moles of potassium iodide. And from moles of potassium iodide, we'll do the mole-to-mole ratio, moles of silver iodide. If I want to know which of these ions stays in solution, essentially which of these ions is in excess, I need to do the same thing now for silver nitrate. I start with the same amount of silver nitrate, 0.65 grams. I'll convert grams of silver nitrate into moles of silver nitrate, and then moles of silver nitrate into potassium nitrate? If I want to know whether potassium iodide or silver nitrate is the excess reagent, it's useful if I convert them both into the same final product. So silver iodide. We looked at other ways that we can determine limiting an excess reagent. Do you guys remember what else we can do to compare these reagents? One of them was take one of the starting materials and convert it into the other, and then see which one of them follows stoichiometry of the balanced chemical equation. But it's a little bit less intuitive. This is very clear. How much of the final end product can I make? All right, so here we need to do a simple calculator exercise. Using our periodic table, we'll calculate the mass of potassium iodide and silver nitrate. Potassium iodide, 39.1 for potassium, 126.9 for iodine, roughly 166 grams in every mole. Sorry, Keon, that one I'll hand that one out in a little bit. Silver nitrate, silver at 107.8, nitrogen at 14, 3 oxygens, 16 each, 48, 169.8. I'll be honest, this was the shortfall in this problem. I didn't think their molecular masses were that close. I thought their molecular masses would be a lot more different, but since you've got silver and iodine, both very heavy atoms, they added up to a lot. Let's look at the top equation. What do I put in this mole-to-mole ratio? What values? 1 to 1. The chemical equation is balanced. So the coefficients are 1 to 1. If I had to go through the work of balancing the chemical equation, then I'd take the numbers that I used to balance. So it's as simple as 0.65 divided by 166, 0.0039 moles of silver iodide can be made from the amount of potassium iodide I have. 0.65 divided by 169.8, 0.0038 moles of silver iodide can be made from the amount of silver nitrate present. This is nearly a perfect amount of each of them that they all precipitate. But which one is actually the limiting reagent? Silver nitrate limits the reaction. It produces a slightly smaller amount of product. So when the question asks which of these ions stays in solution, silver or iodide, is it asking which is the limiting or which is the excess? It's asking for the excess reagent. Which one is left behind? And in this case, it would be iodide. There is not enough silver present to pull all of the iodide out because there's more silver iodide that could be made, but I'll run out of silver iodide based on how much silver nitrate is present. You guys see the imbalance? We calculated it. We've determined our limiting is silver nitrate, our excess is iodide. That means that there's going to be a little bit of iodide left over. Okay, now the question is, how much of that ion is left in solution? Again, there's a nice component here that says all of the stoichiometry is 1 to 1 to 1. So if I could have made this many moles of my product, that means that's actually how many moles of my starting material I had as well. And if I can only make this many moles of my product, That means that's also the number of moles of my starting material that I used. Again, only because the stoichiometry is all 1 to 1 to 1. Otherwise, I would have had to take this number, and I would have had to work it backwards, and I would have had to take this number and convert it. But our stoichiometry worked out really nice here to say, I started with 0.0039 moles of silver iodide. I only used 0.0038 moles of silver iodide. How many moles of silver iodide are left over? A very small amount. 0.1 millimole, if you will, or 100 micromoles. And then, of course, we could do a mole to mass conversion. And we could calculate the mass of the iodide that's left over. Was that something that you guys did? Or did you stop with the number of moles left over? There you go. A very small amount of moles left, but we can actually calculate how many moles are left over based on how many moles could have been produced, how many moles actually were produced. How many moles could have reacted, how many moles actually reacted. We're taking the difference. All right. So we spent the last 2 weeks on reactions. We're going to spend this week talking about gases, and we're going to talk next week on thermochemistry. So I kind of want to open the floor a little bit and hear what information you guys have already, just based on being humans alive in 2025, about gases. What do you know about gases? What is a gas? How can you measure a gas? By the way, I have some worksheets for you guys. Some of them printed stapled, the others are double-sided. Does anybody prefer the stapled? I only have 4. All right, then I'll start with the double-sided, but some of you will get the stapled. You guys don't know any gases? You're missing out. Take a stab at it. Oh, you want a staple? Yeah, I thought you. No, what do you think? Oh, there you go. Gases exert pressure. Not the only thing in the universe that exerts pressure, right? Chemistry exams have been known to exert pressure. How can a gas exert pressure? I'm walking through gases right now. Don't feel a lot of pressure. Staple. Or do you? Anybody ever like laid back into the wind and let the wind hold them up? That's a gas exerting a force on you. That's a gas exerting pressure. Anything else you guys know about gases? Are gases pure substances? Sometimes. How about the gas we're breathing right now? Pure substance? No. Mostly nitrogen, some oxygen, a little bit of everything else. Are gases homogeneous? Usually, unless you're standing like by a bonfire and the smoke is coming in, or unless there's an inversion and you can see the smog hanging in the air, then they're not as homogeneous. You guys know this website? This is the PhET simulator. You can find it by just Googling, literally if you just Google PhET, it's the first thing that pops up. And you can do some of these different interactive things. So right now I have a container. Can you tell me what characteristics we're going to be measuring based on this container. What properties of a gas can I measure here? Keon? Pressure? Temperature? Can I measure the volume? I can kind of gauge the volume. You guys can actually see I've got a handle on this box, and I can pull that or compress it, so I can kind of visualize the volume, but there's not a volume measurement. Anything else? And don't feel bad if you are just reading the list of things, but you may need to look at a different spot in order to understand the last variable of the gas. It's actually here. The amount. The number of moles of a gas. That's another important feature. If I have a lot more moles of gas, a lot less moles of gas. If I have a big volume of gas, a small volume of gas. If I have hot gas, if I have cold gas. If I have gas with high pressure or gas with low pressure. Those are the features of gases that we're going to be studying in this unit. And we're going to see how all of those characteristics of a gas impact one another, and a bunch of the different laws that go around them. So we are starting Unit 7. And this is Module 16, the gas laws. Can you explain to me how a gas exerts pressure? Can you explain to me how you exert pressure? Push, yeah, or run into something, right? And that's really all a gas molecule can do. So gases exert pressure through their collisions. When they run into something, they exert a pressure. So pressure here is equal to the force divided by the area. Shoot, I should have brought this. There's this really cool trick where you can actually harness the pressure of gas by expanding its area. So let's look at this, this little piece of garbage that I just found. This is a little bit heavier on one end than on the other. So I'm gonna hang this out just until it's too heavy and it falls over. So you can see that on its own, it can't just hang off of the edge. And similarly, this piece of paper, it's not that heavy. This could also just fall right off the edge if I let it. But if I hold this piece of paper over this heavy piece of trash, I can actually get it to stay in place a little bit longer. It's not because the piece of paper itself is heavy enough to weigh it down, so much as all of the gas that is sitting on top of that piece of paper is holding this piece of trash in place better. So by expanding the amount of area that I have gas sitting on it, I am expanding the pressure. All right. So let's talk about units for measuring gases. Or rather, pressure. We're going to talk about the scientific units, or like the SI units, the international units. But I also want to talk to you guys about some of the more common ones. The scientific international unit, the SI unit, is pascals, PA. And a pascal is not just its own arbitrary unit. It's actually a unit in several units in trench coats. 1 pascal is equal to 1 Newton per meter squared. Can you tell me what type of measurement meters squared would be? If I told you that I have 30 square meters, I'm talking about an area. So what then is Newton, N? What type of measurement is that? Force, because pressure is equal to force over area, newtons per meter squared. And newtons is a bunch of units in a trench coat. This is 1 kilogram meter per second squared per meter squared. A newton is the kilogram meter per second squared. So that's mass times distance divided by time squared. Okay, some other more common units. Of course, we have the kilopascal, where 1 kilopascal is 1,000 pascals. We have the bar. 1 bar is equal to 100,000 pascals. One bar is equal to how many kilopascals? A 100 kilopascals. 100,000 pascals. 100,000 pascals. Atmosphere is another common unit. Atmosphere is labeled as ATM. You guys know the acronym ATM to mean anything else? Oh, you use it? Oh, yeah. Automated teller machine. Or like at the moment, not a lot going on, ATM. Good. Just see it as atmosphere now, from now on. 1 atmosphere is equal to 101,325 kilopascals. No, you're right. I'm sorry. It's not kilopascals. Thank you for catching that. 101,325 pascals. Let's write that in kilopascals. This would be? Say it with confidence. 101.325 kilopascals. One atmosphere is also equal to 760 millimeters of mercury. And we're going to discuss what millimeters of mercury means in a little bit. But 1 millimeter of mercury is also given the unit 1 torr, which means that we can also say 1 atmosphere is equal to 760 torr. Okay, there's one last unit, but this is not as common in science. So this is more just so that we can connect it to ourselves. Anybody fill up their tires and know the unit? And what's that stand for? What do you fill your tires up to? Just in the winter? What do you fill it up to in the summer? Oh, 32 is probably the lowest you should put your tires at. 35 is a good number. My dad always fills his customers up to 40. But your tire in your car will often tell you different pressures to put it at. That's because the pressure in your tire changes how it rides on the road and how it wears. So softer PSI, you get kind of a smoother ride, but your tires wear out a little bit quicker. Harder PSI, you get more life to your tires. Sorry, we're not talking about tires, are we? Okay, let's talk about measuring pressure. There's two instruments that we're going to talk about. One of them is the barometer. Do you hear the unit? Barometer. Measuring bars. We're going to look at the diagram of this barometer. We've got this upside down tube. And it's sitting beneath the surface of a liquid. At the top here, we've got a vacuum. This is what we call an evacuated glass. So that means that there's minimal amount of gases sitting at the top. This is why when the air on the outside of this system pushes down on the liquid, that liquid wants to go somewhere. So the liquid goes somewhere that's not pushing down on it. The liquid gets pushed up into this tube because there's no gas pushing down on it from the top. And remember that those gas molecules are really just running into the surface of the water. That's what's pushing it. That's the pressure. So if this is vacuum up here, then it's getting pushed up. Now if I take this apparatus and I know that this is my standard temperature, I can take it to a new environment where the pressure is changing, and I can watch how the water level moves up or moves down. If I get the water level to come down a little ways, what does that mean about the pressure on the outside of the flask? The pressure outside is decreasing. I don't have as much air pushing down on the water to push the water higher up into the flask. Now that air is lighter, less pressure, and so the water actually falls down from the glass. Decreased pressure. As it turns out, what we can actually say here is that the height of that water in the glass is proportional to the pressure. This little symbol looks like an alpha or a little fish. Proportional to. Have we used this before in class? Do you guys remember seeing this? Okay. The problem is it doesn't take a lot of pressure to move water a lot. Here you go, Kaden. So trying to make an apparatus like this and measure changes in pressure, especially between places like Salt Lake City and Los Angeles, you'd need a very tall tube of water. So we use mercury instead. More than 13 times as dense. It takes 13 times the amount of pressure to move mercury. So we can have a smaller apparatus and we can measure more gradual changes in the mercury level, and that allows us to report even larger changes overall. The pressure change is then in millimeters of mercury displaced in the tube. If I increase the pressure out here and I make the mercury increase by 1 millimeter, well, I've made it move by 1 torr. If I can get the mercury to move 760 millimeters, or 7.6 centimeters, then I've moved it 1 atmosphere. I've changed the pressure by 1 atmosphere. I want to point out, millimeters mercury should seem like the most bizarre unit of all of these. The other ones, whatever, people come up with weird units all the time, but millimeters of mercury, how am I taking a length and reporting that as a pressure? It's because I'm measuring this length. How much is the mercury moving inside of this tube? That is proportional to the change in the pressure. The other way that we measure our pressures is with a manometer. If barometers measure bars, then manometers measure mans. Now, I don't know why they call it a manometer, to be quite honest. But our apparatus here is to have this type of glass apparatus that has a U-shaped tube at the bottom. And then we fill that U-shaped tube with liquid. I want you guys to look at this setup right now. We've got some gas in here. Perhaps it's a gas that we want. And then this outside is open to the atmospheric pressure. The gas on the inside, similar to the vacuum, this gas is pushing down. I want you guys to tell me, is there a higher pressure inside of the glass bulb where the gas is, or a higher pressure outside of the glass bulb where atmosphere is? Anybody willing to defend their reasoning? Ashley. Yeah, this time there's 2 lines though. So here we said when there's a higher pressure, the water moves higher up. So here, if there is higher pressure on this side, then the water should move higher up on the opposite side. If the gas had stronger pressure, it would be pushing against the atmosphere, and we'd have the opposite. Sorry, your face looked like I confused you, but you had it right. Yes. All right, you guys can probably guess what I'm going to show you. Maybe not. I'm going to draw another example of a manometer where we flip the pressure situation. This little apparatus works a little bit like a manometer. Do you guys remember this reaction? Copper and nitric acid. Is there gas inside of that bulb? Yeah. But now there's more gas coming into the bulb. This reaction is producing a new gas, nitrogen dioxide. That means that we're building gas amount in the flask. We're increasing the pressure, and that gas starts to bubble its way out. Then as the reaction stops, gas production stops, so pressure inside of the reaction flask starts to decrease, and that means the pressure on the outside of this apparatus is stronger, and it pushes the water all the way back up and in. But you didn't think that I could make use of that little Instagram TikTok 3 different ways in your lecture class, did you? Instagram TikTok? Why does it sound really old? All right, let's look at another drawing of our manometer. U-shaped tube. What could I draw the water levels like if the gas was at a higher pressure than my atmosphere? Or sorry, this was just pressure. Let's say that I've got my atmosphere here, atmospheric pressure. Where should the line on this side be drawn? Should it be higher, equal, or lower if I want this to be the higher pressure system? The line should be lower than this. Good. So I'm going to label this as higher pressure inside the flask. And over here, I'll label it as lower pressure inside the flask. Cool stuff, right? Yes, Saint? Good question. We just watched an example. We produced gas, so we created a larger amount of gas, and that increased the pressure. We're actually going to look at how the 4 variables, number of moles, pressure, volume, and temperature, all play a role in this little apparatus. I think one piece I left off of my diagram is that these manometers, they can often have some sort of a stopcock. So that means that I can fill a gas inside of this bulb just on its own, and then I can bring it over to the U-shape glassware where I can already have it evacuated, similar to this, so there is no additional glass. And then I open the stopcock, and I allow the water level in the U-shape or the mercury in the U-shape to equilibrate. If I already know the pressure of the atmosphere, then I can use the difference in the height to determine the pressure inside of the manometer. And in fact, there's actually there's an equation that goes with it. I don't know that you guys will need to use this. We can say the pressure of the gas is equal to the pressure of the atmosphere outside of the system plus or minus H. It depends on whether you want your pressure in the gas to be higher. Then you're going to add the difference in this height level. Or if the gas in your manometer is lower, you're going to subtract the difference of this height level. So this works especially well if your manometer is filled with mercury, right? Because then you can measure the difference between the 2 levels in mercury, and you can use millimeters mercury to calculate the pressure. Yep. All right, we've got these 4 variables of gases. The first is the number of moles, and we give this the symbol N. In fact, this is not just for moles of gas, this is for moles throughout chemistry. We represent the number of moles of something with the lowercase n. We represent the pressure with P. To be fair, I think oftentimes this is written as capital P, but there's no reason it needs to be. If you look at your equation sheets, you'll see that this is written as capital P. So I'm gonna try and stay consistent and write that as capital P. We have volume, which we can write as capital V, and we have temperature, which we'll write as capital T. There are a lot of dead men in this chapter who have their names given to different laws about how these 4 variables relate. So most of these gas laws say, assuming you hold constant these variables, here are how these other 2 variables relate to each other. The gas laws hold some variables constant, and they show how others are related. I'm going to show you how one of these gas laws can be solved. And then for the other gas laws, I'm just going to give you the equations because the solution to the gas law is exactly the same. Let's start with, man, I don't know if there's a good one. Let's start with one that is relatable to us. Anybody else have their low tire signal go off when the weather gets cold? Oh, thank God, it's not just me. What's happening there? Why is your car telling you that your tire doesn't have enough pressure just because it's cold out? Less collisions. Less heat, less collisions. And we said collisions were pressure. So we can write this equation. Pressure is proportional to temperature. Less temperature, less energy, less collisions, less pressure. Okay, but that is not a useful equation. In fact, it's not an equation, right? There's no equality between them. There's just a proportionality. So let's say that I measure the pressure at a specific instance. I'll call this pressure 1. And that pressure is equal to the temperature at that time if I multiply by some constant K. What is K? It doesn't matter, but there is a solution that says the pressure is equal to the temperature if I can just multiply by a random number, right? Then we can say that pressure at some other instant is equal to the temperature at that instant times the same constant, times the same variable K. Okay, this is line 1. 2 instances measuring the pressure and the temperature shows that multiplying them by some constant k sets them equal to each other. Now if I solve for k equals, well, to get k alone, do you agree that I need to divide by t1? K times t1 is equal to p1, so divide by t1 on both sides. p1 divided by t1 equals k. For those of you that are a little bit more visual with doing your calculations, divide by t1, divide by t1. On the right-hand side, t1 cancels out. Can I do the same thing on the other side? Can I set this equal to this constant k? K equals P2 over T2. Okay, if the ratio of pressure to temperature is equal to K in both of these instances, I measure the temperature outside and the pressure of my car and in the summer, and then I come back and I measure the temperature of the temperature outside and the pressure in my car tire in the winter. I can now set them equal to each other because they're both equal to this constant K. So now I get my actual gas law. P1 over T1 is equal to P2 over T2. And this is named the Gay-Lussac's law. Can you tell me what variables are held constant during this gas law? Gay-Lussac's law compares pressure to temperature. If we hold constant what? Berkeley? Volume and number of moles. Exactly. Does the volume of my car tire change between summer and winter? It's still the same tire. It might look a little bit flatter, it might look a little bit taller, but that's just because the material is stretchy. It can change its shape, but it's the same volume. Do I change the number of moles of gas in my tire? Yeah, maybe if I've got a leak, but most tires are pretty rigid. They don't let that air escape. So this example we have of why does my tire say that it's flat in the winter? Because it got cold, that's saying I've got the same number of moles of gas in my tire. I've got the same volume, but the temperature is dropping, so the pressure is dropping. And then you've got this issue, if you pump up your tire in the winter and none of it escapes over the winter, now you get into warm weather and you've got a larger number of moles and the temperature increases, your pressure is going to continue to increase as well. All right, that's the Gay-Lussac's law. Here is the next law. Charles's law is that volume is proportional to temperature. What are we holding constant during Charles's law? Number of moles and temperature? Pressure. If volume and temperature are in here, then my other two are held constant. You can see that these are proportional in the same way that pressure and temperature were proportional. The example here is often take a balloon and put it in the freezer. What do you notice? The balloon will shrink. And then take that balloon out of the freezer, and as it warms up, the balloon will expand again. We get the exact same equation, but we substitute our variables. We get V1 over T1 equals V2 over T2. Boyle's law compares pressure as being inversely proportional to volume. Actually, there's a better way to write inversely proportional, and that's to say that pressure is proportional to the inverse of volume. As my volume decreases, my pressure increases. As my pressure decreases, my volume must be increasing. So now we get a different equation. We could go through and we could give the same proof. We could say that P1 is equal to 1 over V1 times K, which means instead of dividing by T1, I'd need to multiply by V1, and the equation that I get is P1 times V1 is equal to P2 times V2. Do you see the difference in how the gas law is written when the variables are proportional versus when they are inversely proportional? We multiply them instead of dividing them. The last of these individual laws is named for Avogadro. Avogadro's law compares volume being proportional to moles. If you could write an equation here, what would it be? Good. V1 over N1 equals V2 over N2. If I increase the number of moles, I should be increasing the volume. Good example here is actually blowing up a balloon. I should have brought a balloon today. If you blow into a balloon, you are increasing the number of moles. What happens when you increase the number of moles in a balloon? It expands. Increasing moles increases volume. There are two other gas laws, and thank God we ran out of dead men to name them after. So these are named appropriately for what they do. The first is the ideal gas law. We're going to define what an ideal gas is in a couple of modules. But just briefly, an ideal gas is one that behaves the way that these equations write. That usually means it's at a high enough temperature and it's at a low enough pressure. But at too high of pressure, it doesn't behave correctly. At too low of a temperature, it doesn't behave correctly. And this actually combines all of these relationships, plus it gives us a variable. So we get that pressure times volume is equal to the number of moles times a constant, R, times temperature. And this is often pronounced as it's read, as it's written. We call this, pronounce it, Pivnert. We pronounce it Pivnert. It's how you remember what variables go on which side of the equation. Pivnert, PV equals nRT. It's a little bit like VSEPR theory, or VSEPR, but Pivnert, pressure, volume is equal to the number of moles times this constant times temperature. So the only thing we really need to talk about here is R. How many values for R do you think there are? Sure. 3's not bad. There's a lot of different values depending on what units you want to use for pressure, for volume, for temperature, and really there's only one unit for moles. So here are the most common R values. 0.08206, with units of liters times atmospheres divided by moles times Kelvin. Oh, do you see how many units are in there? It's a lot. Which makes it a really good conversion factor, right? If you have any 3 of those 4 variables, you can solve for the 4th. It helps you convert between 3 pieces of known information and 1 piece of unknown information. Liters is telling us which of these 4? Volume, atmosphere, moles, K, temperature. This is Kelvin. All right, the other most common is 8.314 kilopascals times liters over moles times Kelvin. And kilopascals, we know, can be expanded. We can write kilopascals as kilojoules. Because a Pascal, oh no, I'm sorry. I'm getting ahead of myself a little bit there. There is another version I want you to see here. On your equations sheet for the final exam, up on this top right-hand side, you've got this ratio. It says R1 over R2. Actually, just above that, you'll see that R can also be written as 8.3145 joules per mole Kelvin. These two are the same, except for how units of atmosphere and volume are written. Joules is another unit of force. So kilopascals times liters is just giving us joules there. And then I do want you to notice there's this ratio that says if you take these 2 versions of the gas constant and you take them as a ratio, you can get 101.3 joules per liter atmosphere. What does that remind you of? 101.3? That's the ratio between atmospheres and kilopascals, 101.3. So the gas constants have a ratio that reminds you of the conversion between kilopascals and atmospheres. That can come in handy. All right, one last gas law, and then I'm actually going to have you guys work on applying these gas laws. This last one is called the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. What variable is held constant? Only moles. Before I turn you over to the worksheet, I want to point out the usefulness of these equations. Gay-Lussac's law is useful if everything is constant except your pressure and your temperature. If you want to see the relationship between an initial state of a gas and the final state of a gas, you're going to use Gay-Lussac's law if you're analyzing the pressure and temperature of that state. Charles's law, only if you're analyzing the change of the volume and the temperature from an initial state and a final state. Boyle's law, only pressure and volume. Avogadro's law, only volume and moles. The ideal gas law does not analyze a change. The ideal gas law is for any given instance. This is just one instance of a gas. Combined goes back to observing a change. The only difference here is you have a little bit more wiggle room. You can change both the volume, the temperature, or the pressure, but you have to keep the moles constant. Which of these is not like the other? Which of these is not like all of the others? The ideal gas law analyzes one instance of a gas. All of the other gas laws analyze some change that a gas is going through. I wanted to say doesn't analyze a change, but might be better to say only analyzes one instance. Does it make sense to you what I'm saying? Only analyzes one instance? No? Then let me give you a little example so that you can go through it a little bit more easily. Let's look back at this PhET simulator. Now, first I need to pump some gas in. And you'll notice that I'm changing the number of particles, so I'm changing the number of moles. Now let's hold constant volume and I'm holding constant volume and the number of moles. I'm not going to add any more moles in. What law am I using? Gay-Lussac's law. I'm going to look at how pressure and temperature are related, but I'm holding the volume constant and I'm holding the number of moles constant. All right, so let's heat this up. What should happen to the pressure if I heat up the gas? It should increase. Do you see the pressure gauge? Increasing. So what I could have done is measured the temperature before I started and the pressure, and then measured only the temperature after I was done, and I could have calculated for the new pressure. An initial state, part 1, a final state, 2. All right, now what happens if I cool it? What should happen to the pressure? Pressure should decrease. And I can actually calculate it without needing to do any of the measurement. So I can say, I've got a gas at this temperature and this pressure. I want to heat it up to this temperature. How will the pressure be impacted? Initial state, final state. All right, let's hold temperature constant and let's change the volume. I'm going to expand this. All right, let's look at the pressure. Pressure's at about 2.5 gauges. Now let's compress it. What should happen when I compress the volume? Decrease volume. Increase pressure. These are inversely proportional according to whose law? Boyle's law. I went from 2.5 to well over 2.5. Increased pressure because I decreased the volume. My molecules of gas, they're having the same collisions, but they're running into the wall more often, so they're increasing the pressure. All right, now let's hold, this is a little bit confusing in my opinion. Let's hold pressure constant and see what happens when I increase the temperature. Woo! I'm expanding the volume. And we said that was whose law? That was Boyle's law? There's somebody's law. Good work. Increase the temperature, increase the volume. Decrease the temperature, decrease the volume. Notice how the pressure gauge is staying still this whole time. I'm keeping the pressure constant, but I am changing the temperature, which results in the volume changing. Okay, so on this worksheet, you're given a number of different scenarios. You need to determine which of the gas laws is appropriate to use. Which one should you plug your variables into? Look for which variables are changing, which variables are held constant. And you'll notice the title, right? Gas laws. Which gas law is not used? I want you to go through these problems and figure out which gas law is not being utilized in them. Um, I want to give you guys a chance for a break. I also want you to work on this. So over the next 15 minutes, be working on this and be taking your break. At the end of the 15 minutes, we're going to go through it together. Okay? Good snack. Good breakfast. Nope. Which one are you going to start on? Fair. You know, you can start anywhere you want to. Just not the bathroom. Because we're not there yet. Okay, I'm sorry. You shouldn't do number 4 yet. I mean, you might be able to solve it, but I haven't gone over it yet. We don't know if it's volume 1 or volume 2, but as long as we're consistent, we can number it. Let's say that this is volume 1. Volume 1 equals 5 liters. What other information do we need? Good. So that should this be N1 or N2? Good, because it's related to the molecules of this volume. Good. Don't forget your units. All right. Now let's confirm the amount of gas is increased. 1.1. Good. Good. And what about V2? Right, so we can write it V2 equals question mark. You could write V2 equals X. You want to solve for X. All right, which of our laws is going to work here? Great. Now we can rewrite Avogadro's law as is, or we can manipulate it so that it solves for what we want. Tell me what changed I want to solve for what we want. Good. Exactly.
you're laying out what variables are going to be involved in it. This. Oh, yeah, okay, I like it. What can help you identify that is kind of listing out what information you have. So you've got like what temperature, T equals question mark, will this many moles, N equals this, occupy this volume, V equals pressure. Do I have a V1 and a V2? Do I have a T1 and a T2? Do I have N1 and N2? I really just want each of those ones. And the only one I know is each of the ones.
All right, one thing I should have told you. Temperature calculations have to be done in Kelvin. So if you're doing the temperature one, the first thing you have to do is convert it into Celsius. That changes the final answer, depending on whether you're looking at it as temperature in Kelvin or temperature in Celsius.
As soon as I run across a piece of information, I'll kind of write it down in a list. So I know I've got volume, and then I've got moles. And as soon as I get to the later part of this, I'm going to see moles again. Which means these are going to be volume one, moles one. And then I'll be looking at volume 2, moles 2. And that can help you identify what equation is best to run into.
Oh, wait, no, wait.
That's it.
Yep, you will.
I know. I should have practiced that and I forgot to.
Yeah.
But if you know how to do that, then I'd go down and do number 3. Finish with number 3 because that's just a calculator exercise.
Oh, okay.
We can do
So
it
that's,
together.
I was just wondering, like, we're supposed to. You know what I'm saying?
Because we have none values. We don't have a P2 or V2 or P2. Yeah.
Oh, not the way you wrote it. Not the way I wrote it.
Because we have all of them except for
You agree? Good work. Yeah, so it's
I know, it's tedious, not hard, but
I got a question.
yeah.
I see that they all come.
Good.
They're not. Ours, this is
Very
moles times
Oh, okay.
over moles. Oh, okay, so there's a on the bottom.
It is, yep,
So it's kind of like two different points.
it is.
One way that you could write this unit, it seems really weird, is you could say this is 0.08206 liter atmospheres with mole Kelvin on the top. That looks super funky, because you're taking the units of one thing and writing it away from it, but you can. Yep. Thank you.
You bet. All right, just 4 minutes left. If you want to use your break, make sure you get up and stretch your legs. This is the right time to do it.
Looks like a day off. Yeah, this equation.
Pressure times volume is proportional to temperature. Yeah, yeah. There's a lot. Actually, one of the reasons I didn't do this is because there's a lot of things going on. Pressure is inversely related to volume, but pressure is directly proportional to temperature.
So there's like 3 different relationships going on. But you're right. You could have also said pressure over temperature is proportional to volume. You could say volume over temperature is proportional to pressure. So this is one correct way to write it. Okay.
You watch it.
So we want to use which equation? Yeah, this one down here. P1 over T1. Good. You got it.
I'm just throwing together apps.
Yep. The only thing here is we have to convert these into Kelvin to use them. Okay. And this one looks great. Good job. No units here at all. You know why units are useful? They tell you if you're making sense or not, right? If you do a calculation like this without units, you can't actually tell if your units cancel the way you should them to. And that can be risky. And I don't know the answer, but it looks like you've got it set up right. You solved it with R. So you took the ideal gas law, just hit merge.
Yeah.
But I don't. Oh. R is a number with units, liter atmosphere mole Kelvin. You have taken that number and then you've like divvied out its units to be different numbers. I want to give you an example. This is like saying the density of water is 1 gram per milliliter, and then saying 13.6 grams per 22 liters. You're like taking a unit, grams per milliliters, and you're putting numbers in it. Yeah. So what you actually want is to rearrange this equation for T. And you want to plug in this number with its units as is. Because then when 12.3 liters multiplies by this, liters will cancel. Or it divides. This R value allows volume to cancel its liters, pressure to cancel its liters, and moles to cancel. I'm saying liters, I'm sorry. Units. This allows volume to cancel units, pressure to cancel units, moles to cancel units, and it will leave your calculation with just the units or temperature. I got lost here. So you know how all of these 4, they all have their own units. R has all of their units itself, which means that if I know 3 of these 4, I can use R to solve in 4. R can cancel everyone's units. Exactly.
All right, shall we go through them? Is there anything you guys don't want me to erase? You okay with all of it? All right. So problem number 1, I want to remind you guys how I like to pull information out of word problems so that I can digest it a little bit easier. Problem number 1 says volume 5.00 liters of a gas. Okay, that's a volume. So I'm going to write that down as volume. I'm not writing it yet as V1 or V2. I'm just writing it as V because I actually don't know what equation will be useful. Is known to contain 0.965 moles of a gas. if the amount of gas is increased to 1.08 moles. Okay, now I have a second number for moles. So now I know moles is something that's changing. So I'm going to say 1 and 2, which means that my first volume was volume 1. That was the volume with that number of moles. Would it be incorrect to call this V2 and N2? No, not incorrect. As long as you are consistent, it doesn't matter what you call them. You could call this V star and N star, and V triangle and N triangle. It doesn't matter what you call them, be consistent. Then the question is, what new volume will result? Okay, which of my laws is useful for V and N being the only variables changed? Avogadro's law. So if I copy down Avogadro's, V1 over N1 equals V2 over N2, this isn't how I want it to look. I want to solve for V2. So I'm going to do a little bit of algebra. I'm going to multiply N2 on both sides. And I'm doing this so that I can get my equation to look like V2 equals. That's why I'm doing this. V2 equals. And again, if I multiply by N2, then N2 cancels on the right-hand side. I get V1 times N2 over N1. The last thing that I'm going to do is plug my numbers in. The reason that I don't plug my numbers in here is because there's a lot of numbers and they come with units. This is more simplified. It's easier to work around. Now that I've got an equation that I like, I'm going to plug everything in. V2 equals 5.00 liters times 1.80 moles divided by 0.965 moles. Do we anticipate the volume will increase or decrease? Volume should increase because volume is proportional to the number of moles, and moles is increasing. What'd you get? 9.3? 9.33 liters. Volume increased because I increased the number of moles. It didn't matter what temperature it was. It didn't matter what pressure it was. It mattered that the temperature and the pressure didn't change. Those two things remained constant. Problem number 2. In a sealed gas container, the pressure is 235 kilopascals. The temperature is 20 degrees Celsius. If the can is warmed to 48 degrees Celsius, what will the new pressure be? P1, T1, P2, and T2. But we have to do some conversions on temperature. This was a big thing. You should probably put this in your notes a little bit earlier. It can seem really confusing. In fact, the first time I taught this, one of the reasons I still don't have it in my notes well is because this equation is set up where as long as the units are consistent, the math will work out. But those of you that solved this in Celsius have very different answers than those of you that solved this in Kelvin. So that the temperature scale you're actually using matters. Can you imagine why we want to use Kelvin instead of Celsius? What is Kelvin? It is the SI unit. It's also, it's an absolute scale. It says if you have 0 amount of energy in your gas up to an infinite amount of energy in your gas, whereas Celsius, 0 Celsius is just kind of an abstract number. It's when water freezes, but it doesn't tell you about the amount of energy that the gas has. So we have to use Kelvin because it's proportional to the energy. All right, so we get P1 over T1 equals, oh, actually, sorry, I wanted to do that conversion. 20 degrees Celsius plus 273.15 equals 293.15 Kelvin. And 48 plus 273.15 equals 300 and, I don't know, anybody want to help me out? Huh? 321.15? Thank you. All right, now let's plug it in. First, I'll copy down my equation, P1 over T1, equals P2 over T2. Then I'll solve for what I want, which is P2. So I get T2 times P1 over T1. I guess I should have thought about this a little bit easier, a little bit more too. I've given you two very similar problems where the variable you want is on top and you just need to multiply by a variable on the bottom. It's a much harder algebra when the variable you want is on the bottom, because then you need to multiply it to the top and then multiply everything else to the other side. It just takes more algebra. Maybe I'll show you guys an example of how to do that. All right, now we plug it in. P2 is equal to 321.15 Kelvin times 235 kilopascals divided by 293.15 Kelvin. Once again, Kelvin cancels. I'm left with units of kilopascals. What did you guys get? And why should I round to 257? 3 sig figs throughout. Actually, maybe even less. I should have been a little bit better than that. So let's just keep it at these 3 sig figs. Let's say 20.0, 48.0. Yes?
So we don't need to convert kilopascal into atmosphere?
Don't need to convert what?
Kilopascal into atmosphere?
Not at all. Nope. Why? Sure, you can. But if you converted kilopascals into atmospheres, you'd have some dimensional analysis. You'd be multiplying by some number or dividing by some number. The reason that the temperature doesn't scale the same as converting any other unit is because we're not multiplying consistently both of our numbers. We're adding a number. If we were to multiply to convert our temperatures, that would be different. But because we're adding to convert our numbers, it's not an equal shift. Yeah? But no, we can keep this as kilopascals unless it asks us to give the final pressure in atmospheres. But I think you guys understand that's just another dimensional analysis step. There's not any more work going on there. That's new here. We're just doing kilopascals to atmospheres. All right, so let's, I think the next one can wait. Let's do kind of an inserted one. Let's take this new pressure and let's determine the temperature. And let's say, what temperature will it be? 300 kilopascals. I know P1, I know T1, I know P2, I don't know T2. I want to know T2. This is a bit of a solve your own or pick your own journey problem, because I actually have two pieces of information where I have P1 and T1. I know this as P1 and T1, and now I know this as P1 and T1. I have multiple reference places that I can set this to. Are you guys okay with that? So let's take the numbers we just got. 321.15 Kelvin and 257 kilopascals. P1 over T1 equals P2 over T2. I'm going to show my algebra here. I want to solve for T2. T2 cannot be on the bottom. So I need to multiply both sides by T2. Now I get T2 times P1 over T1 is equal to P2. That's very similar algebra to what I just did, but I'm not solving for P2. I want to solve for T2. So I need to divide by P1 and multiply by T1 so that my pressure one cancels and my temperature one cancels. So here I'm multiplying by T1, dividing by P1. The algebra is a little bit more involved, but it's the same process. Get rid of what you have on the left and move it to the right-hand side. So now I have T2 equals P2 times T1 divided by P1. Extra step, no new math, all the same process. And then we plug it in. I'm actually less interested in what the number is. I was more interested in having you guys solve that. Anybody want to give us what the number is? Did anyone solve it? Yeah. Okay, so sig figs was something that tripped us up on the midterm. I had an oversight here because 48 and 20, well, 48 is 2 sig figs, but 20 is just 1. So if I had written this better as 48.0 and 20.0, when I do an addition, and that's the first thing I do before I do any of the multiplication or division. When I do a division, I'm limited to what? Decimal places. So how many sig figs in this answer, assuming that I had 1 decimal place here? 4. Because the first decimal place is the 4th sig fig. 5 is not significant. 0.1 is significant. So I actually get 4 sig figs out of my calculations, where the most sig figs I had was 3. Now when I do this whole thing, I get to have 3 sig figs. I get to have 4 sig figs at the end of all of it. How fun is that? We increased the number of significant figures by doing that addition. Deal? All right. Number 3 was, at what temperature will 0.654 moles of neon gas occupy a volume of 12.30 liters at a pressure of 1.95 atmospheres? I don't have 2 instances of any of my variables. I'm considering 1 instance. What is the one gas law that considers only 1 instance? The ideal gas law. So I'll write this out as PIVNERT. And now to solve for T, I divide by NR on both sides. T equals PV over NR. Which R value do I want to use? And I'm deciding that on the units. I want units of atmosphere to cancel. I want units of liters to cancel. I want units of moles to cancel. So T equals 1.95 atmospheres times 12.30 liters divided by 0.654 moles times R, and again we can choose which unit we want. I'm going to choose the one that has liter atmospheres per mole Kelvin. You know, the way I read those units is actually how they're read. Liter atmospheres, because liters times atmospheres per mole Kelvin. Now let's make sure that our units cancel. Atmospheres on the top divided by atmospheres. Liters divided by liters. Moles times 1 over moles. And I'm left with 1 over Kelvin. What is 1 over Kelvin? Kelvin. Yeah? 2 wrongs make a right. What did you guys get when you plugged this all in? 446.9 Kelvin. And if we wanted to convert that into Celsius to make it more digestible, we would subtract 273.15 Kelvin. Good. Okay. A few more things to talk about with gases. We're actually moving on into Module 17, which is so nice. I wanted to try and get through all of 17 today if possible. Do you guys have questions on these gas laws? Did you identify which gas laws we didn't use? We didn't use a lot. I don't know what I did there. Anyways, I'm going to show you how we can calculate density using the gas law. Oh, did you look at your equation? Which of the gas laws are on the equation? Just the ideal gas law. So I wanted to demonstrate actually that you can get all of the other gas laws out of the ideal gas law. If we said PIV inert describes a gas at any one instance, that means we can do a very similar setup to what we had before. P1 V1 over N1 T1 is equal to R, and R can be equal to P2 V2 over N2 T2, which means that we can set these equations and say P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. All right, now imagine you're given a problem that says the number of moles is not changing. What law is that? The combined gas law. It's right there. It's in the ideal gas law if you set the ideal gas law equal to itself. Now let's say that the temperature doesn't change. What gas law is that? Got Boyle's law? All of the gas laws are inside of the ideal gas law if you just set it equal to itself and then remove the variables that are being held constant. Or you add them to your cheat sheet. Those are your two options. All right. In order to start section 7, module 17, we need to talk about standard temperature and pressure. Yes. We refer to this as STP, standard temperature and pressure. This is defined as 273.15 Kelvin and 1 atmosphere. Sorry. So this is approximately equal to 0 degrees Celsius. Actually, that's exact. And 1 bar. This is approximate. 1 bar and 1 atmosphere are slightly different. But these are what we call STP. So now if we plug in STP into the ideal gas law equation, PV equals nRT, pressure is 1 atmosphere times some volume. Let's say that we're looking at 1 mole of a gas. Times our gas law constant. Times our temperature. When we solve all of this out, we get a volume of 22.4 liters. But we could take it a step further and say, this is the volume of what? Of a mole. This molar volume at STP is 22.4 liters, which is not small. It's actually quite big. And that's just 1 mole of gas. Can you remind me how many, or how big 1 mole of liquid water is? Molar mass of water is 16 plus 2, 18 grams per mole. The density of liquid water is 1 gram per milliliter. So 18 grams is 1 mole. That means 18 milliliters is 1 mole of water. So you're looking at about that much liquid water is 1 mole. And now to get 22.4 liters, if you were to take that mole of liquid water and turn it into gas, it's going to make up, I actually don't have a good scale for you, 22.4 liters. It expands into a huge area. Okay. This can be useful because now we can actually convert between volume and moles of gas. This only works if we're at STP. If we're not at STP, we have to do a little bit more work. But that is to say that I don't have to tell you, I'm going to weigh out 100 kilograms of a gas. When am I ever going to weigh a gas that I'm going to provide in a reaction? Instead, I can say, I'll give you 48 liters of a gas at STP. And now you can calculate how many moles are in that gas, and we can do the stoichiometry that's needed in a chemical reaction. Not all reactions are run at STP, but the ones that are have this new conversion. All right. There is another interesting thing that comes out of gases here, which is density. And their relationship to their molar mass. Okay, let's start by looking at the ideal gas law, PIVNERT. And we'll rearrange to solve for just pressure. Pressure equals nRT over volume. We can substitute for N. The number of moles is the mass of something divided by its molar mass. So we substitute N, and we'll abbreviate. We'll say that P equals M over big M, MM, times RT over volume. If I have mass per volume, then I am reporting the density. So the pressure is equal to the density times RT divided by the molar mass. Do you guys agree that density is mass per volume? So I can actually abstract that M lowercase and V and write it as just volume. And now I've got density times RT is over the molar mass is equal to the pressure. At this point, if we wanted to, we could actually take the pressure, the temperature, and the molar mass. We could solve for the density. But this is actually a useful way of using the density of a gas to solve for its pressure. What I'm going to do is multiply by the molar mass and divide by the pressure. The molar mass is equal to the density times RT divided by the pressure of that sample. Question number 4 on your worksheet was all about calculating the density. What I didn't do a good job of getting to there was showing you how you'll need to use the molar mass of Freon, you have its chemical formula, to convert the number of moles that you have into the mass that you have. So to solve that problem 4 on your worksheet, you'll have to use this equation. And you'll convert it. You'll write density equals pressure times molar mass of Freon divided by RT. And that is actually an equation given to you. This equation up here, sorry, number 6. But I want to I should point this out. You are used to representing density with lowercase d. You'll find that this equation is on the bottom left-hand side. It's got that squiggly m, and it says squiggly m is the molar mass. But then it says is equal to P. It's actually not P. It's rho. So on this equation in here, you're given rho is density. I want you to be familiar with that, because if you don't recognize that symbol as rho, and you don't know that it represents the density, that equation is impossible to use. And again, we can simply rearrange to solve for density, or if we have the density, we can solve for the molar mass. That's what you need to solve this problem number 4 on the gas laws. You can also start working on molar volume of gases 1 and 2. When we come in on Wednesday, we're going to talk about partial pressures for a little bit. And then we're going to look at kinetic molecular theory. We'll wrap up module 17 and 18 and unit 7. All right, keep practicing. And if I can leave you with anything, it's write out your work. When you're doing real chem, when you're doing these practice problems, write out everything, get familiar with that process. Have a good night, guys.